Hey kids, time to talk about Lagrange. You might remember Lagrange from BC Calculus, where we used the Lagrange error um, theorem, boundary, whatever it was, to look for the error bound in using Taylor series. Well, Lagrange made a lot of contributions to math, so we're going to explore another one. So previously, you were finding absolute maxes and mins given a domain region with a boundary. Now I'm going to restrict your domain further to just that boundary, or just really any curve. It doesn't have to be a boundary of a region. It may or may not be, but it certainly really restricts. I mean, we are talking about all infinite sets, but instead of looking inside and in an enclosed boundary, I'm just going to give you one constraint in the XY plane. So look at this function in two variables, right? This is up in Z space. Z, right? I take my domain values, X and Y, multiply them together, add 1, and I get my height. Well, I want to know what are the maximum and minimum values when I restrict your domain to just values that satisfy this equation. X squared plus y squared is equal to 1. So if I look at this is my constraint. And I want to know, what do all of those values that satisfy my constraint, those values are the only ones I can put into here. What does my function do to those domain values? And further, after I figure out what my function does to my constrained domain, I want to know which one of my domain values create maxes and mins up there on the surface that intersects my curve. So let's look at this piece by piece. Here's my domain in the XY plane, right? So I am saying that you can only pick points along this blue curve to put into this function. And then what does that mean? So this entire, right, satellite, hyperbolic, parabolic, blah, blah thingy, just look at this curve right here, this light blue curve here. That light blue curve is a result of using all of these xy's into my function. So it looks like there is a maximum value here, a maximum value here, a minimum value there, and a minimum value here. The question is, which x and y's from my domain created those maxes and mins? That's what I'm after. Was it 0, 1? Was it 1, 0? Was it some other point on this circle? And which ones? I don't want to test them all. That's where Lagrange comes in. He says, I have a method to find your suspects. Your suspects will be from the domain, but instead of an infinite amount of suspects, Lagrange is going to narrow your list, and then you're going to take the list that Lagrange gives you, and you're going to test those values into your function and see which one is highest and which one is the lowest. So a little bit of background to what Lagrange did. We certainly I cannot give you the whole proof, but I can show you a little bit of where what he's doing comes from, and then you're just going to have to take him on faith. I did the proof at some point way 30 some years ago in a total math theory class in college. I do not remember it at all. But the idea is, again, of these level curves, passing level curves through the surface, right, where you make z a constant. When you make z, for instance, equal to 2, right, that's passing that plane through here is going to give me some level curve, right? Don't judge my drawings. And then I can change my z, right? And I get all of the level curves on this surface. Some of them intersect. Okay, I need to stop drawing because I'm terrible. But when you just, what this is a prior objective in this course, if you look down upon this and project those level curves onto the XY plane, they would look like this. And hopefully that's not too big of a surprise, right? Because if I make Z equal to 2, 2 is equal to XY plus 1. That means XY is equal to 1, which means Y is equal to 1 over X. So doesn't these level curves, right? The contour map looks like a bunch of 1 over X's, right? Now, look at the domain circle, though, that I left in there. My domain circle intersects one of these level curves. One of these level curves, I don't know what it is. Z equals, I don't know. But it does intersect. It intersects there, there. Looks like it intersects there and there. Gee, over here it looked like there were 2 maximums and 2 minimums, and over here it looks like there's a level curve. Now, this idea of, right, kissing, right, the level curve and the domain circle, right, kissing right there, they share a tangent line. Each one of these intersection points, they share a tangent line. The tangent line on the domain circle and the level curve, which comes from the surface, are related. Well, if their tangents are related, guess what else is related? Their normals. Their normals are going to be related too. And another prior objective, we just found a way to use partial derivatives to find a normal to a level curve. Do you remember what that was? It started with a G. So here is a picture, right, where I have the tangent line that is shared between the level curve and the domain circle. The tangent line is shared, so are the normals shared. And the normals we get gradients from partials are related. They are scalar multiples of one another. So the gradient of the surface at some points there on the domain circle are equal to a scalar multiple of the gradient of the constraint. That's what Lagrange says. So Lagrange says you're going to solve the system for lambda. Now, you need to be careful here. Notice what G is the constraint. The constraint needs to be set equal to what? 0. Okay. I'm going to expand because this is really 2 vectors. This is an equation. So I'm going to take my vector equation, my equation with vectors in it, and I'm going to expand it out. I'm going to solve a system, and Lagrange is going to give me a suspect list. So here is my surface. Here is my constraint. But remember, I have to take my constraint and set it equal to 0. Well, that's easy enough. Now, think about what that's doing, right? Because in 3D space, what does x squared plus y squared plus 1 equals 1 look like? Right? It looks like an infinite cylinder, right? Can you see my little Pringle-shaped intersection there? So the idea is kind of, right, like you're taking, right, you're just kind of flattening it out so that you're looking at your domain circle down there, right? There you can kind of see the curve. And can you see the maxes and the mins there? Somewhere here, right? So let's do some math. So the first thing I need is partial f. I'm sorry, the gradient of f, which takes my partials, right? So the gradient of f partial with respect to x, partial with respect to y, partials here of the red after I've set it equal to 0, partial of the constraint with respect to x, with respect to y. Set them equal to one another. Y is equal to lambda 2x. X is equal to lambda 2y. No judging how I draw my lambdas. I'm pretty bad at it. And then don't forget your constraint. So I'm going to try to solve this system. The first two equations come from the setting the gradients equal to one another with a scalar multiple. And the last one is my constraint set equal to 0. So this one algebraically isn't too bad, right? I'm just going to use some substitution. If y is equal to lambda 2x, but I have what x is equal to there, y is equal to lambda 2 times x, but x is lambda 2y. So y is equal to what? 4 lambda squared. Y. Get y by itself. This is usually, right, the case we don't consider. Think about it, because if y is equal to 0, what is x? X is equal to 0. Look back at your domain. Is the point 0, 0 on your, right, on your domain circle? Nah, don't need that. Okay. Add 1, divide by 4, square root. I get two values. Lambda is equal to plus or minus 1/2. So then let's plug that back in. Plus or minus 1/2 times 2 times x. So y is equal to plus or minus x. Take this x, plug it back into my constraint. Oops, sorry, this is a plus, isn't it? So x squared plus y squared. Since I'm squaring, it doesn't matter, right? So I get 2x squared minus 1 is equal to 0. 2x squared is equal to 1. So x is equal to plus or minus 1 over root 2, which means y is also equal to plus or minus 1 over root 2. Those are my suspects. Maybe you won't be surprised to recognize that that's where these points are. This one is 1 over root 2, 1 over root 2, negative 1 over root 2, negative 1 over root 2. And the other points that I didn't capture on this drawing, right? Those were my 4 suspects. How do I know who's my maxes and who's my mins? I plug back in to the original. And I think you can see the ones in the first and third quadrant are your maximums. And the one in quadrants 2 and 4 are your minimums. Okay, crazy, right? So that was Lagrange, using Lagrange to come up with our suspect list with a relatively nice surface and relatively nice constraint. Let's do one more of those. Maybe make it a little bit messier. Oh, before I do, I want to formalize Lagrange a little bit. So this is the formal definition of using the Lagrange or multiplier. Right, so it sounds all fancy. Unnecessary conditions for the existence of the extreme value, subject to this constraint, right, where your constraint equation is set equal to 0 because you're down in the xy plane, is that the gradient of your surface is equal to a scalar times the gradient of your constraint for some scalar that is a real number. There's my 2 variable situation. 3 variables looks like that. Remember, this all is because the gradient vectors are parallel. That's what these 2 statements mean. So for 3 variables, right, I just extend to my third. I still set my constraint equal to 0. I still have my gradient of my surface equal to a scalar times the gradient of my constraint. And here's his method. Solve the system. Sounds so simple. This ain't that simple. This can be a big fat dagger. But then when you do, right, this gives us our list of suspects. Critical points, right? And you plug them in to the original surface and identify maxes and mins provided they exist. And in this situation, lambda is called the Lagrange multiplier. So let's try one. Find the max and min of this surface, 5x minus 3y, so up there in z space, given this constraint, another circle, right? So if you want to pause the video and see if you can do this, right, or see how far you get. I don't really ever, I'm not going to ask you this, but I do need to know the extreme value theorem applies, right? But, right, I don't have any places where my partials are undefined. So next I'm going to set up a system with my Lagrange multipliers. So I kind of skipped the step here, right, where I'm finding, right, finding the gradient of f, the gradient of g after I've got this equal to 0. I know it doesn't look like it matters. setting the Lagrange equation up. Oops. Ah, no, my triangles aren't upside down. So 5 is equal to lambda 2x. Negative 3 is equal to lambda 2y. And then my constraint. No, it doesn't really matter. Do the first two, right? Really kind of just look at this one and this one. Isolate and get it x and y, right? You're basically doing substitution. We're going to consider that lambda is not 0. In the last example, I went and did a substitution, but honestly, with my constraint equation like this, I've got both x and y in terms of lambda. I can just take my x there and my y there. Substitute it into the constraint equation. And again, setting it equal to 0 is just making Lagrange happy, as long as it's going to be okay in this situation. So x squared plus y squared had a common denominator. So what is that? 34 over 4 lambda squared, which reduced to 17 over 2 lambda squared, is equal to 136. Solve that for lambda. And I got lambda squared is equal to 1 over 16. Right? Nice numbers, kind of forced that way. So lambda is equal to plus or minus 1/4. Now go back to your x and y equations. Right? For negative 1/4, x was negative 10 and y was 6. If lambda was positive 1/4, I got x is equal to 10 and y is equal to negative 6. Step 7, so this was my list of suspects. Because the extreme value theorem applied, I know I'm guaranteed at least one absolute max and one absolute min. I only have 2 suspects, so plugged into the function, I got negative 68. That must be a minimum. Positive 68 is the maximum, and those are the points where they occur. Let's take a look at this. I don't know if I'm going to be able to be on my screen, huh? Oh, goodness, Lanta. What was it? 5x minus 3y? Is that right? 5x minus 3y. Oh. Whoops. There we go. You can see it a little bit better that way, that plane coming through there. Right, the maximum value is at 10. What did we say? 10 negative 6. Ah. 10, 10, -6 up here. Well, I'm trying. Don't make too much fun of me. There we go. All right. So you can make all kinds of fun of me because I'm not so good at GeoGebra when we meet in our live session. And we will, in our live session, we will do an example, go through an example with 3 variables because that's so much fun. All right. I'll see you then. Thanks for being patient with me.